For the second part of 4.4, I'd like to consider a different vector space for a while. We're used to working in R2, R3, and different R systems, but I'd like us to consider the set of all polynomials of degree 2 or less. You can see that it has a similar structure. R often has that double bar, and the exponent tells you what system you're in. Here, the subscript 2 tells me the highest degree of polynomial we're working with. So here's some examples just to get us, make sure we're perfectly understandable. So for instance, here's a classic second degree polynomial. Here's a first degree polynomial, so that counts. And even just a constant qualifies as a polynomial of degree 2 or less. So I'd like us to think about the basis for this vector space. So what is it we would need to create every polynomial of degree 2 or less? Well, I think we would need at least an x squared, and I think we need an x, and I think we need a constant to work with. And so my standard basis for all polynomials of degree 2 or less includes these three parts. So what does this mean is I can create all three of these examples up here using these three terms. So for instance, this first one looks like I would need 7 of these, plus 3 of these, plus 1 of these. For the second one, I would need 0 x squareds, 5 x's, and negative 7 of these. And for the constant, of course, we would need 0, 0, and 10. So you give me any polynomial of degree 2 or less, and I can build it from those three. Just to give you some heads up, our book and your homework problems, instead of using x, often uses t, and often organizes it in reverse order. It's not that important, but I just want us to start thinking along those lines. So, like our other vector spaces, this isn't the only basis that can work. Turns out, here's a basis for all of P2, meaning if I use these three polynomials with the correct weights, I can create any polynomial in P2. So, here's my question. Notice my 1 minus t squared, t plus t squared, and 1 minus t, 2t minus t squared is here. So my question is, can you find the weights that you would scale each of those by to end up with this target polynomial that I just made up? Great question. So, this sounds pretty familiar to the world we're used to. I need weights in front of something to end up with a final thing, but we're just in the land of polynomials. So this is when I want to introduce you to another word. It turns out P2 is isomorphic to R3. Let's move that 2 down. And isomorphic is a mathematical term that is best thought of as it just acts like it. And so if you think about these polynomials of degree 2 or less, they act an awful lot like vectors in R3. So I think we can see this problem in a unique way. I want to think of these as column vectors that we're used to. And I'm going to build a matrix of those column vectors. And if I structure it like this up here, where I have my constant, my t squared, let's write that first column vector. 1, 0 t's, negative 1 t squares. My second column vector would be 0, 1, 1. And my third one, 1, negative 2, negative 1. My target polynomial on this side will act as my target vector. So we're going to augment this with negative 7, 7, and 10. So So one thing I want to point out right now, when we see polynomials, we see rows. And it would be very tempting to put those polynomials as rows inside this matrix. Do not do that. We're converting them. We want them to act like vectors in R3, and when we use those, we put them in as column vectors. So that's one important distinction to make. Polynomials that are horizontal show up as vectors in columns. Well, I think we know what we're going to do next. We're going to row reduce this RREF. I'll go ahead and throw the final version of that. Thank you, calculator. -5, 3, -2. So solving a system of equations, we would say we would have the final solution here. If we called that out, -5, 3, -2. If this was a matrix equation, we would have my x bar written as -5, 3, -2. But we were actually answering a different question. What weights would I need in front of those polynomials? And that's exactly what we have. If I came back and filled those in, -5, 3, and -2, let's check out a few things. For instance, let's multiply, if we were to distribute this to the constants. -5 times 1, -5. There is no constant here. -2 times 1 is -2. -5, -2, check. How about my t's? None here. 3 t's here. +4 t's here. 3 plus 4. There's my 7. And then finally my t squareds. Looks like I'd have +5, +3, +2. 5 plus 3 plus 2, 10 squared. 10t squared. So we did it. So we answered the question about polynomials by converting them into column vectors. And so this idea of isomorphism in mathematics is you can take a question that is a little more challenging. This would be tough to have figured out if we had just went with some algebraic technique to figure out those multipliers. But converting them into column vectors is very friendly for us. And so solving a difficult question by converting it to an easy question is a classic math move. So we're going to look at another example soon, but I just want to toss this out. Question: what about the vector space of all 2 by 2 matrices? What are they isomorphic to? Are what? Well, what would we need? And I think we saw this in a previous video. What would my basis for all 2 by 2 matrices look like? Well, I'd need a 1 in that corner, a 1 here, bottom left, and bottom right. If I had those 4 matrices as a set, I could create any matrix 2 by 2. So think about it. It looks like M 2 by 2 is isomorphic. I could turn each one of these into a column vector with 4 components. So I could say this is isomorphic to this set of column vectors. So it looks like we've got a basis for R4. All right, last example. So here we are back in P2, and I have a set of 4 polynomials that we're going to use. So got plenty to work with here. My question is, with the correct weights in front of each of those, can we create every polynomial of degree 2 or lower? Well, it looks like we've got a lot to work with. We've got 4 polynomials. Each one has a constant, a t term, a t squared. So let's see how we can pull this off. Well, I think what I'm going to do is let's convert this into a matrix of column vectors. So starting at the top, 1, 2, negative 3t plus 4t squared, we now know is the column vector 2, negative 3, 4, and then here comes the other 3. Well, a common move for us. Let's just row reduce this and see if we notice anything. If we throw this in our calculator, RREF, this 3 by 4 matrix gets converted to this 3 by 4 matrix. And what does this reveal? Well, it looks like I see a pivot in the first and fourth columns, which tells me those are two independent vectors. The two in the middle, looks like we would say they have free variables attached to them, which tells me they are dependent on these other vectors. And so the question, can we create every polynomial of degree 2 or lower with these 4 polynomials? The answer is no. Because I would need, remember, P2 is isomorphic to R3. In order to span all of R3, I would need 3 column vectors, each with their own pivot. So equivalently, I can't span all of P2 with just 2 independent polynomials. So, one thing to notice, if you look back at the original polynomials, you can see why this first one has a 1 and the last one has a 1. Because the first 3 polynomials are each scalars of another one. If you scale the first one by -2, you get the second one. If you scale the first one by -1, you get the third one. So the first 3 are all just similar versions of each other. And that's why my first 3 columns all ended up looking like this.